In the race into space, while the United States set its sights on the moon, the Soviet Union chose a very different path. It launched an ambitious program focused on Venus, known as Venera. The first signals sent back delivered shocking information. Surface temperatures on Venus reached around 475 degrees Celsius, hot enough to melt lead, while atmospheric pressure was about 92 times that of Earth, an environment far more extreme than anything previously imagined. After a long series of failures, the Soviet Union achieved something unprecedented. From grainy black and white images transmitted from the planet's surface to the first color photographs from Venera 13, humanity saw sharp, jagged rocks and a searing orange sky. For the first time, we heard the sound of howling winds from another world. Data collected by the Soviet Union over more than 2 decades fundamentally transformed how we understand the universe. Could this be the future of Earth itself? What did the Soviet Union truly discover on the surface of Venus? Venera 13, launched in 1981 and successfully landing in March 1982, marked the pinnacle of the entire Venera program. The moment Venera 13 touched down, the countdown began under those conditions. Any technical failure would have meant permanent silence. Against all expectations, the spacecraft did more than transmit a signal. It operated continuously for about 127 minutes, nearly 2 hours, a human-made machine surviving and functioning on the surface of Venus exactly as designed. In the history of planetary exploration, this was a record. The first data sent back were not numbers, but images. For the first time, humanity saw the surface of another planet in true color photographs. Not illustrations, not radar-based inference, but light that had struck rock, passed through the atmosphere, and been captured. Venus's surface appeared littered with jagged, sharp-edged rocks scattered across hardened ground. The entire scene was bathed in a deep yellow-orange hue, as if the sky itself were on fire. This was the physical result of a dense, CO2-rich atmosphere, where sunlight is scattered so intensely that it nearly loses all direction. One detail that particularly caught scientists' attention was the absence of clear shadows. On Earth, light coming from a defined source always casts shadows. On Venus, light seemed to arrive from every direction. This revealed that the atmosphere was not only thick, but functioned like a massive diffuser, blurring the boundary between day and night, between light source and object. Venus does not have a blue sky, it has a heavy dome of light. Venera 13 did not stop at observation. A mechanical drilling arm was deployed, penetrating the rock beneath the surface, marking the first time in history that humans directly drilled into the surface of another planet. Analysis showed that the primary material was basalt, a product of rapidly cooled volcanic lava. Basalt is evidence of intense volcanic activity, of a planet that once possessed significant internal heat and continuous surface renewal. Venus is not a static rock scorched into stillness. It is a world that once moved, transformed, and perhaps has not entirely fallen asleep. Then came a moment few expected from a planetary mission. A microphone aboard Venera 13 recorded faint vibrations in the surrounding environment. Not a violent roar, but gentle winds brushing across the surface, subtle tremors as metal components of the lander contacted rock during drilling. These sounds may seem insignificant to the human ear, but scientifically, they were decisive. They confirmed that Venus's atmosphere, despite being dense enough to resemble a fluid, still moves near the surface. This planet is not frozen in absolute silence. Venus is not only hot and high pressure, it is a system where atmosphere, terrain, and internal energy constantly interact. Data from Venera 13 revealed a surface undergoing intense chemical weathering, shaped by long-term exposure to a CO2-rich atmosphere laden with sulfuric acid. This is the result of a runaway greenhouse effect, where heat has been trapped uncontrollably for hundreds of millions of years. If Venus once had water, once possessed more temperate conditions in its distant past, what drove it to its present state? When a planet nearly the size of Earth, with similar material composition, ends in a permanent inferno, how fragile is the safe boundary for truly Earth-like worlds? The color, images, geochemical data, and even those faint sounds transformed Venus from a temperature chart into a world with a voice. But to fully understand that voice, humanity must return to an even earlier moment, the moment when the first spacecraft transmitted images from this planet's surface, even if they were only rough black and white frames. It was there that humanity's perception of Venus truly began to change. Before Venus was seen in blazing color and heard through the faint vibrations of wind, it first revealed itself to humanity in stark, cold black and white frames. In 1975, with the successful landings of Venera 9 and Venera 10, the Soviet Union achieved a milestone that had previously existed only in theory, capturing images directly from the surface of another planet. Not the moon, not a body humans had set foot on, but Venus, an uninhabited world where every physical condition works against the survival of machines. Those first images were constrained by the data transmission technology of the 1970s, by the lander's brief lifetimes, and by Venus's own extreme environment. Yet it was precisely this rawness that made them authentic. This was real light striking real rock, reflecting through a dense atmosphere and becoming distorted before reaching human sensors. The first surprise was not the terrain, but the light. The images showed that Venus's surface was not shrouded in darkness, as many had imagined. Sunlight still reached the ground, even after passing through an extraordinarily thick atmosphere, where pressure is about 90 times that of Earth, and cloud layers extend to nearly 80 kilometers in altitude. Yet that light cast no clear shadows. There was no familiar direction to illumination. Objects appeared evenly lit from all sides. The reason lay in intense scattering within a CO2-rich atmosphere filled with sulfuric acid cloud particles, turning the entire Venusian sky into a vast light diffuser. This effect forced scientists to rethink how solar energy interacts with a planetary atmosphere. On Venus, light itself becomes an environment where human evolutionary intuition no longer applies. Looking down at the surface, images from Venera 9 and 10 revealed relatively flat terrain, scattered with angular rocks, and showing no signs of water erosion. There were no dry riverbeds, no layered sediments, no evidence of oceans or long-lasting rain. Instead, the rock formations bore the unmistakable signature of volcanic activity. Subsequent analysis combining imagery with geochemical measurements confirmed that the landing sites were dominated by basalt and solidified volcanic ash. Basalt is not an unfamiliar material on Earth. It forms when lava cools rapidly and is typically associated with large lava flows and intense volcanic activity. Finding basalt on Venus carried deep implications. The planet once possessed substantial internal heat and an active geological history. It was not a world that died in its infancy. On the contrary, Venus was once violently active, a planet whose surface may have been repeatedly reshaped by global-scale volcanic eruptions. The relative flatness of the terrain also suggests that Venus may have undergone episodes of surface resurfacing, where lava flooded older structures, erasing evidence of earlier geological processes. This stands in stark contrast to Earth, where plate tectonics creates fragmented and diverse landscapes. Through those first images, Venus emerged as a planet where internal energy was released in unfamiliar ways. In 1975, these conclusions posed a serious challenge to existing planetary models. Many hypotheses at the time still viewed Venus as a geologically frozen planet, where internal processes had long since ceased. But the black and white frames from the surface told a different story. They revealed traces of a hot, violent, and prolonged past, one whose consequences remain etched into every rock. If a planet can be transformed this profoundly by atmospheric and energy imbalance alone, then where does Earth's safe boundary truly lie? The images sent back were the final signals, just before Venus reclaimed all of that space for itself. Venus is not only uninhabitable, it is a place where physics reaches such extreme states that even the most advanced engineering achievements of the 20th century are pushed to failure. Here, machines break down because the planet itself allows no compromise. The Venusian atmosphere is the direct agent of that destruction. Unlike Earth, where the atmosphere is thin and plays a regulating role, Venus's atmosphere is a massive, crushing envelope that engulfs the entire planet. More than 96% of it is carbon dioxide, with most of the remainder being nitrogen, along with traces of sulfur dioxide and water vapor. Higher up, from roughly 45 to nearly 80 kilometers in altitude, dense cloud layers filled with sulfuric acid blanket the planet, reflecting much of the incoming sunlight while simultaneously trapping heat with near-perfect efficiency. Beneath those cloud layers, pressure rises rapidly with decreasing altitude. At the surface, it reaches about 90 to 92 atmospheres, equivalent to the pressure nearly 1 kilometer beneath Earth's oceans. In this environment, air no longer behaves like a normal gas. It exerts continuous compressive force on every surface, every seam, every joint. Surface temperatures on Venus, meanwhile, remain remarkably stable, with little difference between day and night. At such temperatures, many metals begin to lose their mechanical strength, welds weaken, and electronic components, no matter how well shielded, inevitably move toward irreversible failure. Against this backdrop, Venera 7 became a remarkable milestone. In 1970, during its descent, the spacecraft's parachute system malfunctioned, causing it to fall freely onto the Venusian surface at an estimated speed of about 61 kilometers per hour. By conventional engineering standards, this impact should have completely destroyed a delicate scientific instrument. Yet, what astonished scientists was that Venera 7 did not fall silent immediately. After impact, it continued to transmit a weak signal for more than 20 minutes. Those signals, brief and incomplete as they were, provided the first direct measurements of surface conditions on Venus. After Venera 7, each subsequent Soviet lander incorporated significant improvements. What makes Venus truly terrifying is its ruthless stability. On Earth, machines often fail because of unexpected events. At such temperatures and pressures, liquid water cannot exist on the surface. If Venus once had oceans in its distant past, they vanished long ago. Water vapor, rising into the upper atmosphere, was split apart by solar radiation. The lighter hydrogen escaped into space, leaving oxygen behind to react with the surface and other compounds. The water cycle collapsed, locking the planet into an irreversible greenhouse state. The wrecks left behind on the surface of Venus, slowly heated and deformed over time, have become silent markers. They define the boundary that current technology cannot cross, while reminding us that science does not advance through uninterrupted victories, but through confronting failure and extracting meaning from it. Venus does not destroy machines senselessly. It forces humanity to understand planetary science more deeply, climate, atmospheres, and the fragile limits of planetary stability. When machines can no longer continue observing, science is forced to stop at the boundary between what is known and what cannot yet be confirmed. And from that blurred boundary, decades of debate have emerged. Debates centered on a fundamental question: which signals are real and which are merely illusions cast by a planet that has crushed every instrument sent to observe it? Throughout the Venera era, Venus was commonly viewed as a hot, dry, waterless world, lifeless and essentially geologically frozen in its final state. The measurements collected by the Soviet Union fully supported that picture. But those data reflected only the end result, not the process that led there. In the 1990s, NASA's Magellan orbiter accomplished something Venera never could, mapping the entire surface of Venus using high-resolution, cloud-penetrating radar. Those radar maps revealed that Venus does not resemble an ancient planet worn down over billions of years. Instead, much of its surface appears geologically young. Vast basalt plains, lava domes, and massive volcanic structures appear in dense concentrations. Even more telling, there are very few signs of old impact craters, suggesting that Venus's surface may have been resurfaced on a global scale in the relatively recent geological past. This lay completely beyond the reach of scientific understanding during the Venera era, when landers survived only tens of minutes to a few hours. Scientists saw flat terrain, but could not recognize that this flatness was the signature of a planet that had been almost entirely renewed. Another layer of insight comes from the atmosphere. Venera measured Venus's atmospheric composition with impressive accuracy. But science at the time lacked the tools to understand its long-term dynamics. The Soviet missions detected sulfur dioxide, yet could not see the deeper connection between the atmosphere and the planet's interior. The most important thing the Soviet Union could not perceive lay even deeper and carried existential weight. Venus may once have been a very different world. Modern planetary climate models suggest that early in the solar system's history, when the sun was weaker, Venus could have had far more temperate conditions. Venera measured the consequences of that divergence, but could not observe the moment when the system slipped out of balance. Another paradox lies at altitudes around 50 to 60 kilometers in Venus's atmosphere. Modern data show that at this level, temperature and pressure are closer to Earth's surface conditions than anywhere else on the planet. The surface is hellish, yet above it exists a physically comfortable atmospheric layer. The Venera missions were not designed to study this region in depth. The Soviet focus was the surface, where the greatest challenge lay in pressure and heat. Yet, it is precisely this middle atmospheric layer that may hold the key to understanding Venus's climate history and how it lost the ability to sustain water. In the end, what the Soviet Union did not realize was not a scientific failure, but the scale of the lesson Venus had to offer. They approached the planet as a technical challenge. Could humans place machines in the most extreme environment imaginable? What the Soviet Union discovered on Venus revealed a brutal reality. A planet dominated by temperatures and atmospheric pressures powerful enough to crush even the most resilient mechanical structures ever built. Through the Venera program, humanity gained not only the first direct visual evidence from the surface of another planet, but also hard proof of an atmospheric system locked into a runaway greenhouse effect. The overwhelming presence of carbon dioxide and winds saturated with corrosive acids stands as clear testimony to a path of planetary evolution that runs completely counter to the conditions required for life. Although they survived only a few brief minutes before being destroyed in that inferno, Soviet landers left behind a scientific legacy of extraordinary value. Venus is no longer a distant mystery. It has become a vast natural experiment, a stark warning about the fragile limits of a planet's biosphere and the future that awaits when environmental balance collapses. The Soviet legacy on Venus is a lesson written in extremes, one that modern science can never afford to forget. About 4.5 billion years ago, Earth was a blazing sphere of molten rock, covered by churning magma oceans amid the chaos of the early solar system. It was a planet filled with toxic gases and magma. Yet life was somehow able to take root. Geochemical evidence shows that the earliest traces of life appeared around 3.8 billion years ago. With no sunlight and no oxygen to breathe, life emerged in the darkness of the deep ocean, around hydrothermal vents where chemical energy replaced light. From simple, single-celled organisms, life began a long evolutionary journey. As the atmosphere changed, the planet nearly froze on a global scale. Life repeatedly stood on the brink of extinction, and then, unexpectedly, the Cambrian explosion unfolded when life diversified into nearly every form imaginable. This is a journey into prehistoric Earth, where we will explore how a chaotic planet gradually became the only living world we know. Earth during the Hadean Aeon, a name derived from Hades, the underworld in Greek mythology, was a world that was nearly impossible to inhabit. At that time, Earth's surface was a glowing ocean of magma, constantly disturbed by asteroid impacts, intense volcanic activity, and solar radiation far stronger than today. Earth's primordial atmosphere was a toxic, reducing mixture of carbon dioxide, methane, ammonia, and hydrogen sulfide. Oxygen, the element closely associated with modern life, was virtually non-existent. Meteor bombardment occurred at a high frequency, especially during the period known as the Late Heavy Bombardment, around 4.1 to 3.8 billion years ago. And then, Earth began forming its first solid crust. The oldest minerals ever discovered, zircon crystals, about 4.4 billion years old, show that parts of the planet's surface had cooled enough for liquid water to exist locally. So where did water come from on a world that was once a sea of fire? Modern science suggests that a large portion of Earth's water came from internal degassing, as water vapor was released from magma and condensed as the planet gradually cooled. The boundary between the Hadean and the Archean marks a fundamental transition. The Archean, beginning around 4.0 billion years ago, was still a harsh era, but stable enough for more complex processes to unfold. The most striking evidence comes from ancient carbon signatures. In sedimentary rock layers in Greenland and Canada, scientists discovered unusual carbon isotope ratios of C-12 to C-13, dated to about 3.8 billion years ago. Increasingly, models show that life could emerge under extreme conditions, especially in environments isolated from the chaotic surface. One key candidate is deep-sea hydrothermal vents on the ocean floor. Here, seawater penetrates deep into the hot crust, reacts with metal-rich rocks, and then erupts back into the ocean as chemically rich, superheated fluids. These environments provide stable chemical energy, catalytic minerals, and microscopic structures, ideal conditions for prebiotic chemistry. More importantly, early life did not require sunlight, oxygen, or an atmosphere like today's. It could form in permanent darkness under high pressure where Earth's surface no longer had a direct influence. Once water stabilized and primitive life had taken hold, the primordial oceans became the main stage for Earth's greatest experiment, where life not only survived but began learning how to sustain itself. Before Venus was seen in blazing color and heard through the faint vibrations of wind, it first revealed itself to humanity in stark, cold black and white frames. In 1975, with the successful landings of Venera 9 and Venera 10, the Soviet Union achieved a milestone that had previously existed only in theory, capturing capturing images directly from the surface of another planet, not the moon. Not a body humans had set foot on, but Venus, an uninhabited world where every physical condition works against the survival of machines. Those first images were constrained by the data transmission technology of the 1,970 seconds by the lander's brief lifetimes and by Venus's own extreme environment, yet it was precisely this rawness that made them authentic. This was real light striking real rock, reflecting through a dense atmosphere and becoming distorted before reaching human sensors. The first surprise, not the terrain, but the light. The images showed that Venus's surface was not shrouded in darkness, as many had imagined. Sunlight still reached the ground, even after passing through an extraordinarily thick atmosphere. Where pressure is about 90 times that of Earth, and cloud layers extend to nearly 80 kilometers in altitude. Yet that light cast no clear shadows. There was no familiar direction to illuminate. Of particular interest is the RNA world hypothesis, which suggests that RNA molecules capable of both storing information and catalyzing chemical reactions may have been a crucial intermediate step before the emergence of DNA and proteins. This effect forced scientists to rethink how solar energy interacts with a planetary atmosphere. On Venus, light itself becomes an environment where human evolutionary intuition no longer applies. Looking down at the surface, images from Venera 9 and 10 revealed relatively flat terrain, scattered with angular rocks, and showing Instead, the rock formations bore the unmistakable signature of volcanic activity. Subsequent analysis combining imagery with geochemical measurements confirmed that the landing sites were dominated by basalt and solidified volcanic ash. Basalt is not an unfamiliar material. On land, radiation could destroy organic molecules in a very short time. Lava flows and intense volcanic activity. Finding basalt on Venus carried deep implications. The planet once possessed substantial internal heat and an active geological history. It was not a world that died in its infancy. Around 2.7 to 2.5 billion years ago, a group of microscopic organisms began tapping into the most abundant energy source Earth had ever known: sunlight. These organisms were cyanobacteria. Through photosynthesis, they used water and carbon dioxide to generate energy, and the byproduct of this reaction was molecular oxygen. When oxygen combined with iron, it formed insoluble iron oxides that settled onto the seafloor, creating rock layers known as banded iron formations. These layers, concentrated between about 2.4 and 2.0 billion years ago, are direct evidence that Earth's oceans underwent a planet-wide phase of oxidation. As oxygen levels in the environment rose, vast numbers of ancient organisms that could not adapt disappeared. This is considered the first oxygen-driven mass extinction in Earth's history. Around 2.4 billion years ago, oxygen began to accumulate significantly in the atmosphere, marking what is known as the Great Oxidation Event. Oxygen concentrations were still low compared to modern levels, perhaps only a few percent of today's atmosphere. But even that was enough to change everything. The atmosphere shifted from a reducing state to an oxidizing one, triggering major changes in the carbon, sulfur, and methane cycles. Methane, a powerful greenhouse gas, was destroyed by oxygen, causing Earth's heat-trapping capacity to drop sharply. Oxygen made aerobic respiration possible, a way of extracting energy far more efficient than anaerobic pathways. From the same nutrient molecule, aerobic organisms could generate much more energy, allowing cells to grow larger, develop more complex structures, and eventually form multicellular life. Oxygen, once a destroyer, gradually became the foundation of complex life. The presence of oxygen in the upper atmosphere also led to the formation of the ozone layer. Yet, what astonished scientists was that Venera 7 did not fall silent immediately. After impact, it continued to transmit a weak signal for more than 20 minutes. Those signals, brief and incomplete as they were, provided the first direct measurements of surface conditions on Venus. After Venera 7, each subsequent Soviet lander incorporated significant improvements. What makes Venus truly terrifying is its ruthless stability. On Earth, machines often fail because of unexpected events. At such temperatures and pressures, liquid water can a starkly opposite state, cold, dark, and almost motionless. Geological evidence shows that Earth has passed through multiple periods of near-global scale glaciation. These extreme ice ages occurred mainly during the Proterozoic eon, particularly between about 720 and 635 million years ago. During intervals when ice may have stretched from the poles to near the equator, The cause of these events did not come from a single shock, but from a dangerous chain of climate feedbacks. After oxygen levels rose sharply, methane, a greenhouse gas tens of times more effective than CO2, was oxidized and rapidly depleted. Once ice began to expand, the albedo effect took hold. Ice reflects sunlight far more efficiently than land or ocean, causing the planet to absorb less energy and cool even further. At the same time, changes in plate tectonics helped push Earth deeper into crisis. The positioning of continents near the equator increased silicate rock weathering, a process that removes CO2 from the atmosphere. As CO2 became locked into rock, the greenhouse effect weakened even more. The result was oceans sealed beneath ice hundreds of meters thick, with some models estimating nearly 1 kilometer of ice in certain regions. Sunlight could no longer penetrate, and gas exchange between the ocean and the atmosphere nearly stopped. The carbon cycle was choked at the surface, and the planet appeared like a dead world, silent, frozen, and still. Beneath this ice, however, hydrothermal vents on the ocean floor continued to operate, supplying steady chemical energy. Cracks in the ice, where faint light could slip through, became microbial oases. Climate models suggest that Earth may have shifted from a snowball state to a much warmer condition in a relatively short geological time. Ice melted rapidly, sea levels rose, and vast amounts of nutrients, phosphates, iron, and minerals were released into the oceans. As the ice retreated, the oceans became richer in nutrients than ever before. While oxygen levels continued to rise, evolutionary pressures that had been building for millions of years suddenly erupted into biological innovation. Organisms that had survived in darkness now emerged into an open world where competition and diversification became the primary driving forces. And almost immediately after the final ice sheets withdrew, life returned and experimented with nearly every form imaginable. This was the Cambrian explosion, a moment when evolution accelerated in a way never before seen in Earth's history. Throughout the Venera era, Venus was commonly viewed as a hot, dry, waterless world, lifeless and essentially geologically frozen in its final state. The measurements collected by the Soviet Union fully supported that picture, but those data reflected only the end result, not the process that led there. In the 1990s, NASA's Magellan orbiter accomplished something Venera never could, mapping the entire surface of Venus using high-resolution, cloud-penetrating radar. Those radar maps revealed that Venus does not resemble an ancient planet worn down over billions of years. Instead, much of its surface appears geologically young. Vast basalt plains, lava domes, and massive volcanic structures appear in dense concentrations. Even more telling, there are very few signs of old impact craters, suggesting that Venus's surface may have resurfaced on a global scale in the relatively recent geological past. This lay completely beyond the reach of scientific understanding during the Venera era, when landers survived only tens of minutes to a few hours. Scientists saw flat terrain, but could not recognize that this flatness was the signature of a planet that had been almost entirely renewed. Another layer of insight comes from the atmosphere. Venera measured Venus's atmospheric composition with impressive accuracy, but science at the time lacked the tools to understand its long-term dynamics. The Soviet missions detected sulfur dioxide, yet could not see the deeper connection between the atmosphere and the planet's interior. The most important thing the Soviet Union could not perceive lay even deeper and carried existential weight. Venus may once have been a very different world. Modern planetary climate models suggest that early in the solar system's history, when the sun was weaker, Venus could have had far more temperate conditions. Existential weight. Venera measured the consequences of that divergence, but could not observe the moment when the system slipped out of balance. Another paradox lies at altitudes around 50 to 60 kilometers in Venus's atmosphere. Modern data show that at this level, temperature and pressure are closer to Earth's surface conditions than anywhere else on the planet. The surface is hellish, yet above it exists a physically comfortable atmospheric layer. The Venera missions were not designed to study this region in depth. The Soviet focus was the surface, where the greatest challenge lay in pressure and heat. Yet, it is precisely this middle atmospheric layer that may hold the key to understanding Venus's climate history and how it lost the ability to sustain water. In the end, What the Soviet Union did not realize was not a scientific failure, but the scale of the lesson Venus had to offer. Around 470 to 450 million years ago, the first plants began to colonize land. They did not have tall, woody trunks like modern plants, but were non-vascular forms that clung close to the ground and lived near water sources. This innovation did more than allow plants to stand upright. It restructured Earth's entire surface. As plants spread, they began transforming bare rock into soil, retaining moisture, fixing carbon, and releasing oxygen. As a result, the atmosphere became increasingly rich in oxygen, surpassing the threshold needed to support large bodies. This set the stage for a remarkable phenomenon. The rise of giants. During the Devonian and Carboniferous periods, oxygen levels are estimated to have reached 30 to 35%, compared with about 21% today. With abundant oxygen, organisms that breathe through tracheal systems, especially insects, could reach unprecedented sizes. Fossils reveal ancient dragonflies with wingspans exceeding 70 centimeters, along with giant spiders and millipedes roaming dense forests. Animals, however, were the force that truly brought land to life. This transition began with fish, which evolved fleshy fins and primitive lungs to survive in shallow, oxygen-poor waters. From them emerged amphibians, creatures of two worlds, capable of breathing air yet still dependent on water for reproduction. The solution emerged with the evolution of reptiles. With shelled eggs, water-resistant skin, and more efficient respiratory systems, reptiles broke free from dependence on moist environments. For the first time, vertebrates truly mastered life on land. They could migrate far from water sources, exploit new spaces, and diversify rapidly in form. Land transformed from a barren surface into a complex network of ecosystems, where plants formed the foundation, insects served as intermediaries, and predators occupied the top of the food chain. During this period, ancient forests formed on a global scale. Woody plants flourished, accumulating enormous biomass. When they died and were buried under oxygen-poor conditions, some of that carbon did not return to the atmosphere, but became locked in sediments, eventually forming coal. The giants of the Carboniferous did not last forever, as oxygen levels declined and climates became drier. Large body size turned into a disadvantage. As tectonic plates shifted, massive volcanic eruptions occurred and climate fluctuated violently. The world of giants faced its most brutal challenge, and Earth entered a sequence of mass extinctions. Over the past 500 million years, Earth has experienced at least 5 major mass extinctions. The most severe extinction occurred at the end of the Permian period, around 252 million years ago, commonly known as the Permian-Triassic event. Geological evidence shows that approximately 90 to 96% of marine life and more than 70% of terrestrial species disappeared. But when previously dominant groups collapsed, ecological space opened on a global scale. And in that context, reptiles, organisms that had quietly adapted to dry and unstable environments, began to accelerate their evolutionary pace. Unlike amphibians, reptiles have water-resistant skin, protective shelled eggs, and physiological systems suited to harsh climates. These traits did not make the Permian-Triassic catastrophe easier to survive, but they became decisive advantages in the post-extinction world: hotter, drier, and more unstable. As forests declined and open landscapes expanded, reptiles did more than survive, they spread. This was followed by the Triassic and Jurassic periods, when reptilian lineages diversified rapidly. Some became bipedal predators, others evolved into massive herbivores, and several branches adapted to life in the air or the oceans. This was the period when dinosaurs emerged and gradually came to dominate the land. They were not perfect organisms, but the result of millions of years of evolutionary experimentation in a post-catastrophe environment where the speed of adaptation mattered more than long-term stability. Notably, each mass extinction does more than eliminate life. It reshapes the direction of evolution that follows. Large size, efficient metabolism, or flexible reproductive strategies can all become keys to survival, but only for a limited time. As environments continue to change, those same advantages can turn into burdens. The Mesozoic era, often called the Age of Reptiles, was not a peaceful time. Although dinosaurs dominated for more than 160 million years, the planet remained in constant flux. Sea levels rose and fell, climates oscillated, and continents drifted apart. Their dominance endured not because of stability, but because of an ability to withstand continuous change. From the very ashes of the dinosaurs, another path would emerge, a path leading to mammals and ultimately to humans. Around 66 million years ago, a brief moment brought an end to the era of creatures that had dominated Earth for more than 160 million years. After the Chicxulub impact, the sky darkened, the climate was thrown into chaos, and food webs collapsed. But as fine dust settled and sunlight returned, the planet entered a fundamentally different phase, a world left open, absent of giants. Throughout the Mesozoic era, they were small, nocturnal creatures, living in the ecological shadow of dinosaurs. Fossils show that most mammals at that time weighed less than a few hundred grams and survived through stealth, flexibility, and rapid reproduction. Within 10 to 15 million years after the impact, mammals underwent a powerful diversification. From insect eaters and herbivores to carnivores, from burrowers and tree dwellers to coastal species. This was a slow but persistent expansion, unfolding against a backdrop of climates and landscapes being reshaped. One key factor was the brain, as anatomical data show that many mammal groups began to gradually increase the ratio of brain size to body mass. A larger brain did not immediately mean intelligence, but it enabled behavioral flexibility, learning, and rapid adaptation to changing environments. At the same time, plate tectonics continued to reshape the planet. Continents drifted, new mountain ranges formed, ocean currents shifted, and regional climates changed. These changes created ecological mosaics, diverse environments existing side by side that promoted species divergence. Tropical forests, grasslands, temperate zones, and deserts expanded in turn, each presenting a different survival challenge. Mammals, with their ability to regulate body temperature and care for their young, proved especially well suited to these challenges. Around 7 to 6 million years ago, as Africa's climate became drier and forests fragmented, one branch of primate mammals began adapting to upright, bipedal walking, which allowed longer distance vision, freed the hands for carrying food and tools, and reduced direct exposure to sunlight. Fossils show that brain size increased step by step, accompanied by significant biological costs, high energy demands, longer developmental periods, and slower reproduction. Without the extinction of the dinosaurs, would this path have existed at all? Our existence, therefore, is not an inevitable result of evolution, but a fragile product of a chain of chance events stretching across tens of millions of years. Journeying backward through time into Earth's prehistoric past is not simply an exercise in reconstructing a world of molten rock, toxic atmospheres, or long-extinct entities. From the quiet primordial oceans, where the first photosynthetic bacteria silently released oxygen and completely reshaped the planet's chemical balance. To the rise and fall of colossal species that once dominated the continents, that past has been permanently etched into every layer of sediment and every fossilized skeleton buried deep within the Earth. These geological records are living diaries, bearing witness to an unchanging rule. Life always finds a path through even the harshest upheavals of the planet. Understanding prehistoric Earth allows us to recognize that humanity's existence today is not a given, but the result of a chain of chance events and extraordinary acts of adaptation by life over millions of millennia. By looking into that distant past, we not only uncover answers about our own origins, but also come to understand the fragility and immense value of the ecosystems we inhabit today. In the end, the journey into the past becomes the only true key to seeing the present clearly and accurately anticipating future scenarios, helping humanity protect the delicate balance of our one and only shared home in the vast universe. Did you know that Mars was once considered a planet with real potential for life, only to collapse rapidly afterward? The contrast between Mars's past and its present remains one of the great mysteries. Across the Martian surface, probes have discovered ancient valley networks, dried-up riverbeds, and fan-shaped deltas. Geological structures that can form only when liquid water flows steadily over long periods of time. What did ancient Mars truly look like? The data show that these features are evidence of a wet past that lasted for millions of years. Mars was once active, continuously reshaped by geological and climatic processes, and it carried conditions strikingly similar to those of early Earth. And to understand the fate of Mars, we must turn back time, returning to an era when the red planet was still functioning, still evolving, and still writing its own history. Between about 4.1 and 3.7 billion years ago, during the Noachian period, Mars appeared as a completely different world. It was a young, dynamic planet with conditions capable of sustaining stable liquid water on its surface. At this stage, Mars's core was still extremely hot, and thermodynamic models indicate that the planet's iron-nickel-rich metallic core had not yet cooled enough to stop convective motion. This magnetic field acted as a shield for survival. protecting the young atmosphere from a solar wind far more intense than it is today. Volcanic activity at the time occurred on a planetary scale, and massive structures such as the Tharsis region began to form, releasing large amounts of carbon dioxide, water vapor, and other volatile gases into the atmosphere. Estimates suggest that atmospheric pressure during the Noachian may have ranged from several hundred millibars to over 1 bar, compared to roughly 6 millibars today, only about 0.6% of Earth's atmospheric pressure. With a sufficiently thick atmosphere and higher average temperatures than those of the present, the water cycle began to operate. Rain fell onto the young basaltic surface. Water gathered into flowing streams, carved deeply into the landscape, and formed rivers, lakes, and broad basins. This conclusion is drawn from thousands of geomorphological features observed from orbit. Dense, branching valley networks, especially in the ancient southern hemisphere, whose shapes are almost identical to long-term erosion river systems on Earth. Their degree of branching, depth, and widespread distribution indicate that water flowed repeatedly over long periods, possibly lasting hundreds of thousands to millions of years. Even during the Noachian, its so-called Golden Age, hidden limits already existed, like a silent countdown clock that no one at the time could yet recognize. The Noachian period came to an end, but it left its mark on the surface of Mars. What remains locked within the rocks is an objective geological record, waiting to be deciphered. On Mars, minerals are chemical records frozen in time, preserving evidence of environment, temperature, acidity, and even the slow, labored breathing of a planet in transition. One of the most important discoveries in more than 2 decades of Mars exploration is the widespread presence of phyllosilicates, also known as clay minerals. Spectral observations from the Mars Reconnaissance Orbiter show that clays are strongly concentrated in ancient terrains dated to more than 3.7 billion years ago. Chemically, phyllosilicates form only when basaltic rock interacts with liquid water over long periods in neutral or mildly alkaline environments. On Earth, clays are considered natural catalytic surfaces, places where organic molecules can attach, concentrate, and react with one another. For this reason, when phyllosilicates are observed on Mars, an unavoidable question arises. If prebiotic reactions ever had a chance to occur beyond Earth, could this have been one of the most suitable places? As time passed, the chemical signatures on Mars began to shift in a troubling direction, with sulfates increasingly appearing instead of clays, forming in more acidic environments, often associated with sulfur-rich waters and intense evaporation processes. Acidic environments make many complex chemical processes more difficult and are far less friendly to stable organic structures. On Earth, such environments can still host life, but they tend to be far more specialized and limited. Then there are carbonates, and in theory, if Mars once possessed a carbon dioxide, rich atmosphere, and stable liquid water, carbonates should have been widespread, much like on Earth. Yet on Mars, carbonates are found only rarely, appearing locally in just a few regions such as Nili Fossae. The scarcity of carbonates is itself a powerful clue that Mars's climate system did not operate like Earth's, and that its ability to self-regulate over long timescales may have been weaker from the very beginning. But minerals tell us only about conditions. To understand how water truly behaved, we must look to the places where ancient flows carved their history deep into the surface of Mars. One of the strongest lines of evidence lies in the valley networks, ancient valley systems that blanket large regions of the southern hemisphere. Seen from orbit, their shapes are immediately familiar. Branching structures where smaller tributaries merge into larger channels, closely resembling river systems carved by prolonged rainfall on Earth. Geometric analyses show that these forms are consistent with steady, repeated flow erosion acting over long periods of time. Hydrological models indicate that to produce the density and depth of these valley networks, Mars would have required rainfall or surface runoff sustained for at least hundreds of thousands of years, and in some regions, possibly several million years. This forces us to confront a fundamental reality. Liquid water on ancient Mars was not a rare, fleeting exception. Jezero crater offers an even more subtle line of evidence. Roughly 45 kilometers wide and once held an ancient lake. What makes Jezero remarkable is the fan-shaped delta along its western rim. Layer upon layer of sediments, with grain sizes that decrease from bottom to top, reveal deposition in calm or slow-moving water. On Earth, such structures form over thousands to tens of thousands of years as rivers carry sediments into lakes or seas. Data from the Perseverance rover confirm that the rock layers within Jezero display sedimentary characteristics consistent with stable water environments, not violent flood events. This is precisely why Jezero was selected as a prime location in the search for ancient biosignatures. Farther toward the equator lies Gale Crater, a vast basin 154 kilometers across, with Mount Sharp Aeolus Mons rising at its center to nearly 5 kilometers in height. This mountain is not the product of tectonic activity or volcanism, but rather a massive stack of sedimentary layers deposited over time. Analyses from the Curiosity rover show that many of these layers formed in lake environments marked by repeated wet-dry cycles. Based on the thickness of the sedimentary layers and estimated deposition rates, the lake within Gale Crater may have persisted for millions of years. An environment stable enough for complex chemical processes to unfold. All of this evidence leads to a single conclusion. Ancient Mars sustained an active water cycle over extended periods. If water remains stable for so long, if lakes and rivers endured for millions of years, then one question naturally follows. Did Mars once possess an ocean, particularly in its northern hemisphere? The hypothesis of an ocean in Mars's northern hemisphere begins with a simple yet haunting observation. The planet's striking hemispheric dichotomy. The northern hemisphere lies, on average, about 4 to 5 kilometers lower than the southern hemisphere, forming a vast depression known as the Northern Lowlands. On Earth, elevation differences of this scale are commonly associated with ocean basins. Some topographic maps derived from data collected by Mars Global Surveyor and the Mars Reconnaissance Orbiter reveal winding boundary lines stretching thousands of kilometers, shapes that closely resemble ancient shorelines. Various models estimate that if such an ocean existed, it could have covered between 20 and 30% of Mars's surface and contained a volume of water equivalent to a global layer several hundred meters deep. This is where the debate intensifies. Unlike coastlines on Earth, these proposed boundaries in Mars's northern hemisphere are not perfectly level. This inconsistency has led many scientists to question whether they truly represent shorelines, or whether they are instead the result of erosion, crustal deformation, or other geological processes. Complicating matters further is volcanism and lava flow. As Mars's northern hemisphere experienced massive volcanic eruptions over billions of years, lava may have flooded across the surface, filling in and concealing ancient structures, erasing or distorting the original traces left by water. There is also the hypothesis that the northern lowlands were not carved by water at all, but formed by a colossal impact early in Mars's history. An impact of sufficient scale could have created a global topographic imbalance, which water and ancient climate processes later repurposed as a temporary basin. In this scenario, the ocean, if it existed, was not the cause, but a secondary consequence of a pre-existing structure. Even so, water balance models indicate that the total amount of water required to produce all the observed rivers, lakes, and sedimentary deposits is enormous. If water had existed only locally, confined to isolated basins, sustaining a long-term, planet-wide hydrological cycle becomes far more difficult to explain. At present, there is no firm consensus that Mars once possessed a global ocean in the same sense as Earth. Yet the possibility of very large bodies of water, perhaps shallow seas, existing during certain intervals of the Noachian or early Hesperian periods cannot be ruled out. To maintain such an ocean, ancient Mars would have needed a climate that was both warm enough and stable enough. How, then, did ancient Mars manage to retain its heat? Climate models suggest that Mars's atmosphere during the Noachian period may have been rich in carbon dioxide and water vapor, two fundamental components of the greenhouse effect. If atmospheric pressure at the time reached several hundred millibars or more, carbon dioxide could have retained enough heat to raise surface temperatures close to, or even above, the freezing point of water. However, carbon dioxide alone was not sufficient, as three-dimensional climate simulations indicate that even with a thick carbon dioxide atmosphere, Ancient Mars still struggled to achieve stable global average temperatures above 0 degrees Celsius. This has led to the hypothesis that the greenhouse effect must have been amplified by other factors, so-called secondary greenhouse gases, that played a critical yet elusive role. One of the most important candidates is hydrogen. In a dense atmosphere, collisions between hydrogen molecules and carbon dioxide can produce an additional greenhouse effect far stronger than carbon dioxide alone. Recent models suggest that just a few % of hydrogen in the atmosphere could raise surface temperatures by tens of degrees Celsius. Hydrogen is light and easily escapes into space, so to maintain it, ancient Mars would have required a continuous supply, and this is where volcanism enters the climate story. Intense volcanic activity in Mars's early history may have released not only carbon dioxide and water vapor, but also hydrogen and methane. These gases, though short-lived, could have generated climatic warm pulses, periods of elevated temperatures sufficient for ice to melt, water to flow, and lakes to form. Viewed this way, ancient Mars did not need to be consistently warm like Earth, but may instead have experienced a fluctuating climate, with alternating warm and cold phases. Another factor often overlooked is dust and clouds. On modern Mars, dust can either cool or warm the planet, depending on conditions. In a thicker ancient atmosphere, water ice clouds or carbon dioxide clouds could have acted like a thermal blanket, reflecting infrared radiation back toward the surface. Some models suggest that clouds at the right altitudes could have contributed significantly to heat retention. Although this mechanism remains highly debated. Taken together, these hypotheses lead to a crucial conclusion. The climate of ancient Mars was not simple, not linear, and not permanently stable. It may have been the result of a delicate balance among many interacting factors: atmosphere, volcanism, gas composition, clouds, and even planetary orbit. If climatic conditions once allowed water and energy to coexist, did life ever seize that opportunity? From a biological perspective, the minimum conditions for life on ancient Mars appear to have once come together. Water existed for extended periods. Energy could have been supplied by sunlight, by chemical reactions between water and rock, or by hydrothermal activity beneath the surface. Fundamental elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur have all been confirmed to be present in the Martian crust. However, having conditions does not mean having life. This is a boundary science must firmly maintain. There is no direct evidence that Mars ever hosted living organisms, no fossils, no fossilized cells, no undeniable biosignatures. Yet if life did emerge on Mars, the most plausible scenario would involve simple microorganisms, similar to bacteria or archaea on early Earth. Such organisms would not require oxygen or complex ecosystems. They could have lived in water, within sediments, or even deep underground, where they would have been shielded from radiation and surface climate instability. On Earth, organisms like these still exist today in the most extreme environments. From the deep ocean floor to rocks buried kilometers below the surface. For this reason, modern missions focus on searching for ancient biosignatures, indirect traces that life may once have been present. The Perseverance rover was designed precisely for this purpose. It drills, collects, and stores sedimentary rock samples in Jezero crater, an environment that was once rich in water and well suited to preserving biological traces. Its instruments analyze rock structures, organic compounds, and chemical relationships that could point to past biological processes. This reflects a deeper reality. Life is a fragile phenomenon, not an inevitability. Even when initial conditions seem right, life may never arise, or may arise only to vanish quickly. On Mars, the window of habitability may simply have been too brief. As the climate deteriorated and water became scarce, any early biosphere, if it ever existed, could have been erased before leaving clear, lasting evidence. Earth benefited from its size, a strong magnetic field, plate tectonics, and long-term climate recycling over billions of years. Mars did not. It may have offered an opportunity, but it could not protect that opportunity long enough. What, then, transformed Mars from a planet with biological potential into the barren world we see today? In its early history, Mars once possessed a global magnetic field generated by a core dynamo, similar in principle to Earth's. This dynamo operated while the planet's molten metallic core was hot enough to sustain vigorous convection, producing electric currents and a magnetic field that enveloped the planet. But Mars is far smaller than Earth, with only about half the diameter and just over 10% of the mass. A smaller size meant faster heat loss as the core gradually cooled. Convective motion weakened. The dynamo slowed, then shut down entirely, and the magnetic shield surrounding Mars disappeared. From that moment on, Mars was no longer protected by a strong magnetosphere capable of deflecting high-energy particles from the Sun. Instead, the solar wind began striking the upper atmosphere directly. Light molecules, hydrogen and oxygen, were ionized, pulled away, and swept into space. This was not a sudden event, but a slow, persistent process that unfolded over billions of years. NASA's Mars Atmosphere and Volatile Evolution Mission, or MAVEN, has provided direct and quantitative evidence of this process. MAVEN measures present-day atmospheric escape rates and traces them back into the past, revealing that Mars has lost a substantial portion of its atmosphere since its magnetic field weakened. During periods of heightened activity from the young sun, when ultraviolet radiation and solar wind were far more intense than today. The rate of atmospheric loss may have been many times greater than it is now. The crucial point is this: an atmosphere is not just air to breathe, it is a planet's thermal blanket. As the atmosphere thins, pressure drops. As pressure drops, liquid water becomes unstable. And when liquid water disappears from the surface, the entire climate and geochemical system collapses in a domino effect. Here, the magnetic field was the foundational condition that allowed all other conditions to exist. Mars may have had water, greenhouse gases, and energy, but it lacked a magnetic field long enough to keep all of those elements together over billions of years. Earth did, and this single difference led to two radically different destinies. A planet may gather all the ingredients for life, but without long-term mechanisms of preservation, everything remains temporary. And it was precisely when the magnetic field weakened that an irreversible chain of events began to accelerate. The atmosphere thinned, average temperatures fell, and liquid water vanished from the surface. The first and most decisive sign was the decline in atmospheric pressure. As the atmosphere was gradually stripped away over time, surface pressure fell below a critical threshold. From a physical standpoint, liquid water is stable only within a limited pressure range. On modern Mars, average surface pressure is just about 6 millibars. This means that liquid water on today's surface can scarcely exist for more than a few minutes. As pressure began to drop in the past, liquid water on Mars became increasingly unstable. Lakes slowly dried up, and rivers turned intermittent, flowing only seasonally or during brief climatic cycles. The final episodes of flowing water may have occurred during short-lived, warm pulses, but these became rarer and weaker over time. Eventually, the hydrological system, once a vivid sign of a functioning planet, collapsed completely. Alongside pressure, global average temperatures also declined as the atmosphere thinned. The greenhouse effect weakened, and heat escaped into space more rapidly. Mars did not simply become colder. It lost its ability to regulate temperature. Day-night temperature differences grew extreme. Freeze-thaw cycles fractured the surface. Yet there was no longer enough energy to sustain stable liquid water. Today, radar data show that Mars still holds substantial reserves of water in the form of ice, especially at high latitudes and within subsurface layers. But ice does not behave like liquid water. It does not carve rivers. It does not redistribute energy, and it does not sustain complex geochemical cycles. The moment of collapse, therefore, was not the complete disappearance of water, but the disappearance of water in its liquid state. And when liquid water vanished from the surface, there were no longer rivers or lakes to regulate temperature. No longer cycles of deposition and erosion to renew the landscape, and no longer stable environments for prolonged chemical reactions. Mars shifted from an active planet to a state of kinetic freezing. From a systems perspective, this was the collapse of an interconnected network. On Earth, localized collapses have occurred. Global glaciations, major climate upheavals. But the planet recovered thanks to its size, strong magnetic field, and plate tectonics. Mars did not get a second chance, and when we look back at this process, the difference between Mars and Earth is no longer a technical detail. but a boundary between two planetary destinies. To see that boundary more clearly, we must place the two worlds side by side, comparing each factor, each protective mechanism, and each small divergence that produced enormous consequences. When Mars and Earth are set next to each other, what is most striking is how similar their beginnings were. Both formed from the same protoplanetary disk about 4.54 billion years ago, composed of silicate rock with metallic cores. Both endured heavy bombardment, intense volcanism, and both once possessed water. The most fundamental difference was size and mass. Earth benefited from scale, a strong magnetic field, plate tectonics, and long-term climate recycling. Mars did not. This comparison shows that life does not only need to be born, it needs to be protected. And that is why, when we look at Mars today, we are not simply seeing a dead planet. We are seeing an alternative version of the path that Earth did not take. What we have observed confirms a fundamental truth. Ancient Mars was not a dead planet from the very beginning. It was once a highly active world, equipped with the essential mechanisms that could support life. From a thick, heat-retaining atmosphere to flowing liquid water that shaped the planet's surface. Yet the history of Mars is also an epic of decline. As the planet's core cooled and its magnetic field weakened, the door was opened for the solar wind to strip away its protective atmosphere, bringing a green era to a definitive end. This collapse delivers a core lesson in planetary science. Life is not a self-sustaining state, but the outcome of complex geological defense systems. A world can shift from paradise to a frozen desert within a brief slice of cosmic time. When we look back at Earth, what happened on Mars no longer feels like a distant story from another planet. It becomes a scientific mirror reflecting our own limits. If the fundamental balances that sustain life today were to be disrupted, could our planet follow the same path as its red neighbor? Ancient Mars, therefore, is not only a key to understanding the past of our solar system, but also the most serious warning about the future of our own home. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.